Bonjour, mesdames et messieurs. It's my great pleasure to be here and talk about a little bit a different subject, bringing together geometry and statistics in another way, simply by having the data take values in a manifold. In this case, it's going to be a very simple manifold, just a circle. And we want to do some statistics, we want to compute some statistics for this data. And the statistic we are going to compute is the mean, the simplest statistic, if you like. I should say that this is a joint work with my PhD student, Florian Kelma, and a bachelor student who contributed basically half of it with his bachelor thesis, Johannes Wi, who is in the audience. So, oh, yeah, that doesn't work. Oh. Sorry. So, assume that you're giving data, Z1 to Zn, which are circular. And this might be just wind directions that you have measured here at Palaiseau, and you might be interested in knowing what is the mean wind direction here at this university. Now, the problem with this is that the circle is not a vector space. Okay, so it doesn't make sense to use the usual definition of the mean as being an average, because you can't average on the circle. So what can you do? Well, the simplest thing maybe to do is you embed the circle, say it's a unit circle in the complex plane. Now in the complex plane, of course, you can average. You average your data Z1 to Zn in the complex plane to get Zn bar, the Euclidean average, if you like. Now the problem is that this Euclidean average, here the red point, if these are your data points, then the red point no longer is on the circle in general. But nonetheless, it specifies a direction, right? And you get the point back by projecting onto the circle, just by dividing through by the modulus of your Zn bar. And that's then what is called the circular mean. You can do the same thing with the expectation, of course, and you get your circular population mean. There's one problem, rather, and that is if you're unlucky, your Zn bar may be on the origin. And at the origin, of course, this projection is not well defined. And every direction is equally well representing these data. And so you might say that you get a set of circular means, and which is the whole circle, S1. Okay, well, just how it is. Same for the expectation, of course. Now, what I want to do here, what this talk is about, I want to construct confidence sets for this circular population mean set on the circle. The classical approach of doing this is, not surprising, by asymptotics. Of course, the Euclidean sample mean Zn bar fulfills the central limit theorem, because this is the circle is a bounded set, so you have random variables on a bounded set. This will fulfill a multivariate central limit theorem. Now the projection outside of 0 is differentiable. You can apply the delta method. You get a central limit theorem for the projection, and this is just written down here compactly. Note that the variance, the asymptotic variance, is going to be small, either if the numerator here is small, which means that you have a small variance perpendicular to the mean direction, and it's going to be small if the length of the Euclidean population mean is going to be large, which means that it is close to the circle, and then of course you have less variability. Okay. Now, of course, if you have a central limit theorem, you can derive from it an asymptotic confidence interval. This asymptotic confidence interval is going to be symmetric around the circular sample mean by an opening angle plus minus delta A, which you can compute just as usual. Okay. This gives you an asymptotic confidence set of level 1 minus alpha if you take the according quantile from the standard normal distribution. There are two problems with asymptotics. One problem is that you don't guarantee coverage if you have a finite sample size. It's always the problem with asymptotics. You don't know how many data points you really need for this to be at least approximately true. And the other problem is, in this case here, that you don't know in advance whether the true population mean, the expectation of Z, is going to lie on the origin, and you don't have this property of being able to project out. And so, well, you could maybe pretest for this, but then if you were a careful statistician, then you would say, then I need to do a post-test analysis afterwards. Of course, nobody does that in practice, right? This is complicated. So what I would like to have is indeed a confidence set which is universal in the sense that you don't have to make any assumption about the expectation of Z being not at 0. If it is indeed, then the confidence set should just be the whole circle. And it should not be asymptotic, so it will work for finite. It guarantees coverage also for finite sample size. And the way to do this is to use a test. You test all the possible population means, and then you use the acceptance region of that test to get a confidence region. Okay, the key ingredient to this is Hoeffding's inequality, is a mass concentration inequality for bounded variables. So assume you have bounded random variables on an interval A to B, then you can bound the probability of the average being away from the population mean being larger than t by some quantity that you can compute. And then, of course, in practice, you're doing it the other way around. You start by saying this should be, let's say, at most gamma, the probability that you want to bound, and then you calculate the t so that you know the probability being further away than this t from the true population mean is at most gamma. This t can be computed numerically, at least for this expression. And as long as the gamma, the probability that you want to guarantee, is in a certain interval, which essentially means that you have enough data points, n is large enough. Okay, so if you now want to construct such a confidence region, we first have to test the hypothesis that the expectation of Z is 0. We choose an appropriate quantile from this, or appropriate critical value from the Hoeffding inequality. And the idea is simply that if you have the circle, then the projections, the horizontal and vertical projections, are bounded random variables taking values in the range of -1, 1, of course, right? And so you can guarantee, if you choose this S0 properly, that the probability of the real part of Z n bar being larger than S0 under the hypothesis that its mean is, its population mean is 0, is at most alpha over 4. Similarly, you can bound the probability of it being, the real part being less than minus S0, that is on being on this side. Now you can guess that you can do the same for the imaginary part being above or below. So if indeed the true expectation of Z is 0, then the probability of Z n bar being outside this square is at most alpha. Now you can conclude that it being having a larger modulus than square root of 2 S0 is also less or equal than alpha. Right? So it's very simple. Now if the expectation of Z you're hypothesizing is not 0, then you can write it as some lambda times zeta. Zeta is now the corresponding population, circular population mean, and lambda is some parameter larger than 0. So it's this picture. Then similarly, you can bound the probability on being after rotation, the negative real part of Z n bar being further away than S0 as being less or equal than alpha over 4. Now, for the imaginary part, you can bound this now by 3 over 8 alpha to be on this side with a different critical value SP, which is smaller than S0. That's kind of the reason why one does it this way. And on being on this side, you don't have to bound it away in this direction, because this is anyway the direction in which you're going to project. Right, so you only need 3 directions in this case. And then the difficulty, if you want to go from the test to the acceptance region, is you have to be able to compute the acceptance region. So you need to know what the acceptance region is here. So the question now is, given data Z n bar, which are the zeta which you cannot reject? Right? Of course, the critical point by rotation, you can easily see. The critical case is if Z n bar is just on this strip, right? On the boundary of this strip. And then you can compute this angle very simply by a simple calculation, and then you know essentially what the opening angle for this confidence region is going to be. So summarizing this construction, well, if you have too few data points, so you can't compute these critical values, or if Zn bar is too close to the origin, then you just get out the whole circle, because you can't say anything. Otherwise, again, you get a symmetric confidence region around the circular sample mean, mu n hat, which is governed by this angle delta h. Now, this angle delta h depends is of the order of 1 over square root of n, just as in the asymptotic case. And if your true expectation of z is not 0, so that you have a unique circular population mean, then the probability of inadvertently having the whole circle, so a trivial confidence region, goes to 0 exponentially fast. So essentially, this is not going to happen if n is large enough. And if Zn bar is large, then from this formula here, you can see that delta h is going to be small. So if your data, if you observe an average which is close to the boundary of the circle, then the data should be concentrated, and this is taken into account. But the variance perpendicular to this direction, whether it's large or small, you don't control. And of course, this will play a role too if you want to have a small confidence region. So, but you can also estimate the variance by a similar trick. If you go into the direction perpendicular, you might think this is the y direction, and you consider the squares of the y's, those allow you, under the hypothesis, to estimate the variance, so give an upper bound on the variance, again by Hoeffding's inequality, since these are bounded random variables too. And then if you do this, you can use a different inequality by Hoeffding, which takes the variance into account as well. Putting this together, you get a sharper critical value in the perpendicular direction by estimating the variance. So the details are in the paper, if that was too quick for you. And so you get another confidence region. This is kind of the second construction, taking the variance into account. Under the same circumstances as before, you get the whole circle, and otherwise you get a somewhat smaller opening angle for the confidence region. So to illustrate this with two toy examples, let's start with a favorable situation for the asymptotics. You have just 2 point masses at plus minus 10 degrees, if you like, with a probability 1/2 each. Then the expectation is going to be very close to the boundary. It's 0.985. And if we start with we want a nominal coverage of 1 minus alpha is 95%. And we have 400 observations in each experiment. We repeat this 10,000 times. What do we get? Well, the asymptotic confidence interval region has an opening angle of plus minus 1 degree. On average, the construction with the variance taken into account is roughly twice as large. And if you don't take the variance into account, it's much larger. Okay. Of course, the asymptotic confidence region in this case essentially fulfills the nominal coverage of 95%, whereas the other ones are conservative. This is, of course, due to the fact that you're guaranteeing coverage also in the finite case, and it's a conservative construction anyway, so that's not surprising. The second simulation is less favorable for the asymptotics. So here we have 100 observations from a distribution where we have 3 points, which is concentrated on 3 points. One is just below 0 degrees with 95% probability. With 1% probability, you're somewhere up here, and with 5% probability, you're on the opposite side, so that the expectation of z comes out as 0.9. So it's still highly concentrated. Here we are aiming for 90% nominal coverage. And let's see what happens. Well, for the asymptotic confidence, it only covers with roughly 60%. So we're aiming for 90%, but asymptotically, if you use the asymptotic construction, you just get 60% out, which is horribly bad. Of course, it means you can't, the guarantee is not very good. The construction that we have, of course, guarantees coverage, well, it's very conservative. You get 100% coverage, essentially. But the opening angle is plus minus 5 degrees, so it's quite reasonable still. Right? Whereas if you don't take the variance into account, it's just too large. All right, so to sum up, you can construct such universal non-asymptotic confidence sets if you use mass concentration inequalities and you take the variance into account. That can be done as well. And they have, obviously, they guarantee coverage, which might go wrong on such a set as a circle easily, even if you have 100 data points. I hope you agree. What is open, or has been left open, is how to do this on spheres. You could, of course, do the whole construction, try to make it higher dimensional, but are there smarter ways of just extending this? And it would be interesting to see whether one can do that for other kinds of means of the circle, intrinsic means, which are minimizers of squared arc length instead of squared chordal distances. That's for the future. Thank you.
Okay, thank you very much. I guess we have time for several questions, if there are any. So perhaps one quick question. You mentioned that you had in mind the generalization to higher dimensional spaces like spheres.
Yes.
Would that make sense also to kind of generalize this approach for the rotations using quaternions, or using this special structure of the unit circle among the complex numbers?
You mean if we're going to the S3, say, and use quaternions? Well, I mean, all you need here, what is needed here for the complex plane ions, I only used to have a compact notation for the circle. Right? I mean, it's not essential. I mean, it's essentially I'm using that it is R2. It's just for notational, for having a quick notation of what the angle is and everything. You can write it down in rotations more easily on the slides, but there's no essential feature being used from the complex numbers here.
You don't use the
so you don't need to
multiplication,
use, so this should work in any dimension without problems in any real dimension.
Thank you very much.